Hello everyone, welcome back to Math 110. Today we'll learn about an important topic of differentiation called implicit differentiation. Until now, we have considered functions like this. Y equals sine of x. Let's fix this s. Or let's say we are given a function like this. We can easily write y in terms of x even if we are not given a variable in terms of another, we can easily turn them into a variable in terms of another and take the derivative. Let's say we find the derivative of y. Similar case occurs here. But sometimes that isn't the case. Sometimes we cannot turn one variable in terms of another. We cannot write one variable in terms of another variable. Like, for example, here we wrote y in terms of x. We can't always do that. Let's see an example where we can't do that. Consider this function. Usually they are connected by an equation, something like this. Let's consider this equation. And we are asked to find the derivative, let's say. How do we do that? Can we write y in terms of x? No. You can try, but you cannot write y purely in terms of x, like this, only in terms of x. So how do we find this? The idea is just to differentiate the whole expression. This is called implicit differentiation. The idea is to differentiate the whole thing. Let's see. We differentiated both sides. That's just because the differentiation of a constant is 0. So the derivative of 0 is 0. So how do we differentiate this in terms of x? What is this? This is 3x squared. What is the derivative of this? Since we have two things, y is a function of x. We are considering that because we are to find the derivative of y. So we have to do the product rule here. That is, consider these two things as separate expressions. Okay, let's first take the derivative of this one. What is the derivative of 5x? It's just 5y squared minus 5x. What is the derivative of y squared? It would be, since y is a function of x, it would be 2y dy dx. I use the chain rule here. And what would be this thing? Just the same, 3y squared plus, this is the derivative of, this is 0, so it's 0. The derivative of a constant is 0. So we have an expression like this. Now, what do we need to do? We need to filter out the dy dx so that we can find the derivative of y. So how do we do that? These two expressions are independent of dy dx. So let's get them to that side. So and these two expressions have dy dx as common. if we take dy dx as common in these two expressions, we have minus 5x plus 3y squared. And if we take it to that side, this is 5y squared minus 3x squared. Okay, let's shift over to this side. We erase this part. So, this is the thing we need to find. Let's take it to that side. So, dy dx would be 5y squared minus 3x squared divided by minus 5x plus 3y squared. This is the derivative of y with respect to x. The procedure we did, the thing we did is called implicit differentiation. Usually we are given to find the derivative or gradient of y at, it's also called the gradient. So we are sometimes told, say, find the gradient or derivative at, let's pick a point 1, 2. So let's find the gradient at 1, 2. What does that mean? This means we're putting the value 1, 2. In place of x, we are plugging in 1. In place of y, we are plugging in 2. Let's see what happens. If we plug in 2 here, 5 times 4 minus 3 minus 5 times 1 plus 3 times 4. It's something like minus 17 by 8. So this procedure is called implicit differentiation. Now we'll look into an application of implicit differentiation, which is called logarithmic differentiation. It's a very useful technique to find the derivative of a function when you have a variable as an exponent or as a power. That is, let's see what that is. Logarithmic differentiation. It's an application of implicit differentiation. So, what is logarithmic differentiation? I said this is very useful when you have an exponent as a power. Maybe something like this. X to the power x, or when you have a variable as an exponent. It's a very useful technique. So how do we do that? Let's say we have a function y sine of x. How do we find the derivative of this function? Here, notice we have sine of x as an exponent. So we are to use the logarithmic differentiation technique. That is, take natural log of y, so natural log of y, natural log x, log of y, sine x log x. This is a very useful, this is the main reason why we use the logarithmic differentiation technique. What is this? This is a formula, very popular formula in logarithmic differentiation, that is x to anything will be log of x. So there is that, and it's now very easy to take the derivative of these two because we can use the product rule here and the chain rule here. Let's say, how do we take the derivative of these two? Log of y log x what is the derivative of log of y? 1 over y, as it's a function of x, so the chain rule, it's a product rule, so derivative of sine x is cosine of x. And log of x plus, what is the derivative of log of x? Natural log of x, it's 1 over x. So 1 over y dy dx cosine of, why am I writing cosine all the time? Cosine of x log of x plus 1 over x sine of x. Wait, we have a value for y, which is, let's put the value of y so that we have everything on the right hand side in terms of x. So y cos of x log of x 1 over x sine of x. So if you put the value of y, which is x to the power sine of x, our derivative would be something like this. So using this method, we can easily find the different derivative of a function where we have a variable in the exponent.